partial adjustment model. Here the star is considered as expected term. That means expected. So yt star it's equal to beta naught plus beta 1 xt plus ut. This is equation number 1. So this is expected consumption depends upon the income. Income is explanatory variable here, that is xt. Yt minus y, actual consumption minus uh, current consumption minus actual previous year consumption is equal to del of yt star minus yt minus 1. Yt star is expected value and yt minus 1 previous year actual value. T minus 1 is previous year actual value. The desired level of capital is not directly observable. So Nurlov postulates the following hypothesis known as partial adjustment of stock adjustment hypothesis. Here lambda delta it's in between value in between 0 and 1. So delta it's a known coefficient of adjustment. So delta it's known coefficient of adjustment, and yt in this line yt minus yt minus 1 is actual change, and in the next line equation 3 yt star minus yt minus 1 is desired change, and this line yt minus 1 is equal to it. It's investment. It's equal to it is equal to del of y star minus yt minus 1. That is expected minus actual. It's investment in it's investment in time period t. So from equation 2 we can write as yt minus, from this line yt minus 1 is equal to del yt star minus yt minus 1. Yt is equal to just from the left hand term it's replaced in the right hand, yt equal to yt minus 1 plus del yt star minus del yt minus 1 common, and in the bracket there is 1 minus del plus del yt star. So yt equal to del yt star plus yt minus 1 into 1 minus del. So here observe value of the capital stock. It's the average of desired capital at time period t and capital of previous period. From the above equation, and delta and 1 minus delta being the weightage, putting the value of yt star, that is expected value, from equation 1 yt it's equal to del of beta naught del bracket beta naught plus beta 1 xt plus ut plus 1 minus del yt minus 1. So this equation, put the value here and also use yt star value in the equation, in this equation, and ultimately we get yt it's equal to del beta naught plus del beta 1 xt plus del ut plus 1 minus del yt minus 1 yt equal to del beta naught plus beta 1 xt del plus 1 minus del yt minus 1 plus ut. The partial adjustment model resembles both quake and adaptive expectation model in that it is an auto regressive. In all these three models emerge yt minus 1 as one of the explanatory variable, but in the disturbance term it's most similar that the other two models. So the thing is, partial adjustment model, there is also the term yt minus 1 that is also present in the adjusted model as well as adaptive expectation and quake model. And this partial adjustment, adaptive expectation, and quake model is also called the autoregressive model. Auto means that the term yt it depends upon yt minus 1. That means current period consumption is depends upon previous period consumption, or current period depends upon previous period. That is why it is called auto. And the estimation of the autoregressive model in the first quake model considered, then adaptive expectation consider, after that combine the two model and get the partial adjustment model. First, in case of quake, yt it's equal to alpha into 1 minus lambda plus beta naught xt plus lambda yt minus 1 plus ut minus lambda ut minus 1. In adaptive expectation model, yt is equal to gamma beta naught plus gamma beta 1 xt plus 1 minus gamma yt minus 1 plus ut minus 1 minus gamma ut minus 1. The term yt minus 1 common, same in the two model, and the partial adjustment model yt equal to del beta naught plus del beta 1 xt plus 1 minus del beta yt minus 1 plus del ut. So ultimately quake model consider del yt minus 1, adaptive expectation model consider 1 minus gamma yt minus 1, and partial adjustment model consider 1 minus delta yt minus 1. So both quake and adaptive expectation model, yt depends upon yt minus 1 as well as partial adjustment model, yt depends on yt minus 1. There is a relation between current period and previous period. So classical least square may not be directly applicable because of two reasons. First reason is the stochastic explanatory variable, presence of stochastic explanatory variable, and possibility of seasonal serial correlation. If we want to apply classical least square, it must be shown that the stochastic explanatory variable yt minus 1 is distributed independently of the disturbance term vt. So here vt is equal to ut minus lambda ut minus 1 in model 1, and in model 2, this is model 2, model 1 quake model, adaptive expectation model 2, there is vt it's equal to ut minus 1 minus gamma ut minus 1. If ut satisfied all the classical assumption, VT will not satisfy all the classical assumption. So here error term, it's related with YT, that can be shown that VT is equal to UT minus lambda UT minus 1. Expected value of VT minus 1 is equal to expected value of VT, means UT minus lambda UT minus 1, and UT minus 1 is means UT minus 1 minus lambda UT minus 2. So it is equal to minus lambda, these two terms, expected value of UT minus 1 square, it's equal to minus lambda expected value of UT minus 1 the square is equal to sigma U square. So ultimately it is expected value of VT minus 1, it's not equal to 0. So error term, it's in adaptive expectation and the Quake model are autocorrelated. Secondly, there Secondly, YT minus 1 appears in the Quake model and adaptive expectation model. This YT minus 1 is correlated with VT, and the covariance of YT minus 1 VT, it's equal to covariance of YT minus 1 VT, means VT minus lambda UT minus 1. Sorry, UT minus lambda UT minus 1. So that is covariance of YT minus 1 comma VT. It's equal to covariance of YT minus 1 UT minus lambda UT minus 1, that is ultimately not equal to 0. So explanatory variable in the regression model, it's correlated with stochastic disturbance term, and if we apply Welles, then there is the estimator not only be biased but also inconsistent here. So the result is inconsistent. Even if increase in the sample size, it will not converge, it will be inconsistent. And if YT minus 1 and VT correlated and VT it's equal to UT minus lambda UT minus 1, and in YT minus 1 has a term UT minus 1, then YT minus 1 and VT correlated, there is an instrumental variable. So we can use instrumental variable here. So ultimately there is a problem of bias and inconsistent result. Uh, how to solve this problem? We need, because of YT minus 1 and VT correlated, then we use instrumental variable. So model of instrumental variable, that is YT, it's equal to gamma beta naught. Suppose we have a model YT is equal to gamma beta naught plus gamma beta 1 xt plus 1 minus gamma YT plus, sorry, uh, suppose consider that YT it's equal to gamma beta naught plus gamma beta 1 xt plus 1 minus gamma YT minus 1 plus VT. So Welles cannot be used in this model because as YT minus 1 is correlated with VT, we know that VT is equal to UT minus 1 minus gamma into VT minus 1, that is T minus 1 in adaptive expectation model. So we have to use of proxy for yt minus 1. Here in this case we use xt minus 1 as a proxy. So that is yt equal to gamma beta naught plus gamma beta 1 xt plus 1 minus gamma xt minus 1 plus vt. So in the adaptive expectation model previously we see that yt equal to gamma beta naught plus gamma beta 1 xt plus 1 minus gamma yt minus 1 plus vt. Here if we use proxy for yt minus 1, here we can use xt minus 1. That can be written as yt it's equal to gamma beta naught plus gamma beta 1 xt plus 1 minus gamma xt minus 1 plus vt. So here proxy is this. But the problem is that xt and xt minus 1 are correlated. There is a problem of multicollinearity. This method is known as instrumental method.